Hello, welcome to another problem session. Uh, I wanted today lay the groundwork for an important class of problems that you will encounter in the rotation chapter, and they're called a fixed axis rotation. When you have a fixed axis rotation, axis remains fixed as it is saying. So there are a whole bunch of problems that fall into this. Then there are other kind of problems we'll address later, which is equally important in all exams and contests, what have you. It's called rolling motion. And rolling motion without sleeping. And this we'll do in a later video. So in the fixed axis rotation, you can say pure rotation. So this is a pure rotation. So you can have a ball which kind of rotates about this axis, which is fixed. It's not axis is not tilting or anything, it just remains fixed, and this thing is going around like that. A wheel which is kind of suspended as a pulley, for instance, and maybe you attach a mass, you apply a force like this, and this pulley is kind of rotating about the axis, which is you can say axis which is going through the center. So this axis is fixed. So these kind of problems you probably seen quite a bit better with. Another can be like here is a door and here is a hinge, and the door kind of closes this way and comes out like that. So door is rotating. And where is the axis for that door? Axis is, that's the axis as fixed. In all of these, axis is not moving or rotating. Contrast to a wheel of a car, for instance, a bicycle wheel. It is rotating, and the whole thing is moving at the same time. It's over here at some other time. So you can see the axis used to be here, and now axis is over here. So axis moved. Remained parallel here. Remained parallel in this case. But you can also imagine that there is a wheel here, and you have some shaft, and this whole thing is going to go around, rolling around. So you can see the axis used to be, the wheel somewhere here is, wheel somewhere here is facing that way. And you can see the axis here was that way, axis here is that way. So the axis actually changing direction. So these problems we are going to address at later time. These are simple problems where the axis is fixed. In this case, angular momentum about the axis, angular momentum about the axis is actually, so if you take this axis as a z-axis, this axis is a z-axis, this axis is a z-axis, so this simply is going to be k hat LZ. That's how it's going to be. So and k hat will not change, so we can just deal with this all the time. And if, for a rigid body, this can LZ can be simply written as I Z about the Z axis, ZZ omega Z. The body is not changing around, so this is, I can just say axis here, just to be, you can have x-axis, y-axis, and just drop this completely. So that's the normal way of writing it, like L is simply I times omega, and understood that axis is fixed, so we don't have to really worry about it. So how do you talk about direction, because this is a vector? So the direction, we just say use right hand rule, and say it's the clockwise or counterclockwise. So this is the way we take care of the direction. Okay, so what's the dynamics? Dynamics comes from dl dt equals to torque. And you may remember torque is just R cross F. So in case of rigid body rotation about a fixed axis, this just simply turns into, using this just turns into I for rigid body, I for rigid body. Distribution of the mass is not changing. I is independent of time, fixed in time. Whatever it is, it will remain. And so this is d omega dt, and the torque is and for rigid bodies only external forces torque matter. Okay, so this becomes the defining dynamics for rigid body. Sometimes in a non-calculus courses, this is not written like that. This is the angular acceleration, so you just write it like I alpha equals to tau external. But I want to make sure that you know that this is in these categories. If the problem is in that category, doesn't apply. Okay, this will all fail in that category. So you really need to first know which category of problem we are dealing with, and we can be in a simpler setting like this. Okay, so let's look at maybe one problem just to make sure we understand this. Okay. Okay, so let's look at an example that here is a bar that will illustrate that example, that problem, and we draw a nail through it, and we are holding it right now, and this will be the axis about which it will rotate when we let go. So first we're holding it t less than 0, hold in place, and t equal to 0, let go. So at some time this will be at some time it's going to be in that direction. This have gone over that, and at this instant we want to write the equation for that instant. This is at some time t. So this is at the center, and this used to be the center over there. So at this time I want to write, so the problem is write equation of motion at instant t. So that's our problem, and this kind of thing will show up later in other problems. That's why I'm preparing you for this. So first thing to do is really look at forces, external forces. So here is this guy has a mass m, so this is mg, acts at the center. So this is one of the external force. There is of course this thing is not falling down, so there must be some force here to balance it, right? So that's the normal force from the pin, F of the pin. And these two forces are definitely not equal, because the center of mass is actually accelerating down. So this guy is a little bit more than that guy. You can imagine the pin was not there, the whole thing will be falling down and not rotating like that. It's going to be accelerating down like this. So there is a force there. Okay, so in terms of equation, you'll have this is angle theta at time t. So we have omega. The definition is omega is d theta by dt, and the equation is I about the axis times d omega dt is a tau net. Okay, this is about axis. So that is the equation of motion we're trying to illustrate, right? So omega put in there, it's going to be I about the axis d square theta dt square equals tau net. Or I can say R about the axis alpha equals to tau. Either one of these is fine for now. Okay, so we need to find this, and we need to find this. Well, about that axis we have this, and I will not change whether it's in that direction or that direction. It's I about that axis, I of the bar about that axis. And so we need I about this axis, and that axis is the edge of a bar. So if you look it up, equals I of a bar about edge, and axis through edge, and perpendicular to bar. So this is the axis. And if you look up, it's going to be 1 over 3 ml square. I didn't give the L. You need the L for the bar. So we got this. This is going to go over there. How about the torque? Now this force is right through the axis. So torque of F pin will be just 0. Now we have this force. To figure out its torque, we can just figure out the lever arm. So this is the R for this. This is the R vector for this force, R for mg, and this is the line of force for mg. And when I drop 90 degrees to that, this is the lever arm. So that lever arm, and this distance is L over 2. But this distance is not L over 2. At this time, angle is theta. So this is, you can see that this is base. So this is tau of mg is mg. This is the magnitude. Mg times L over 2 cosine theta, which is a function of time here. So, and the direction is going clockwise. so clockwise. When you have a clockwise direction, then we say the axis actually pointing away, or its axis is this axis. If you want to call it z-axis, z-axis is in that direction. So if I wanted to write tau with a mg along the z-axis, this is going to be minus mg L over 2 cosine theta of t. Okay, so this theta is written with respect to that z-axis. So all of this, if I write down now in here, and so all of this together, you can see I'm able to write it 1/3 ml square d square theta over dt square equals minus mg L over 2 should be sine. Okay, just say from here to here, that distance is, if this is L over 2 and this is theta, then this is cosine theta. Yep, this is cosine theta of t. Of course, this equation is really hard to solve, but I just got an equation of motion. So this is the equation of motion. We can look at another example. Let's look at another example. Okay. So another example, a simple example, is of a pendulum that's in moving in this plane, so it's in this plane. It's just moving back and forth like that, and this is at some instant t, and I want to know what the equation of motion. So what is equation of motion of this pendulum? Okay, now when you look at it as a rotation problem, the axis of this object is like that. So this is the axis about which you might say this whole body, this string or bar to which this mass is hanging from, this whole thing is one system. And so it's kind of like a bar problem, right, in a way, but it's just a mass is over here and not anywhere else. Okay, so if you now work out what's the L for angular momentum is, and say this is the z-axis. So z-axis is pointed that way. So LZ is going to be just I omega function of time, and I is all of mass is located at the distance L from the axis, so m L square, and this will be just d theta dt, and so dl z dt is going to be m L square. C is constant. So in this problem of fixed axis rotation of the rigid bodies, is always going to turn out like this, and a great simplification. So now we need dlz dt is tau z external. So that on this body you have one force and second force, so two external forces. T goes right through the axis, so to get this, we get this tau of the t is 0, then tau of mg Now mg is from here, you drop, this is the r perpendicular for the mg, so you line of force mg, and from the axis you drop perpendicular, and that's the lever arm for mg. And you can see the mg is trying to do clockwise, which is going to be minus, and if you use this angle, then we're looking for this distance same as that distance, and so it's L times sine theta. So this minus mg L times sine theta. So along the z-axis I need a minus sign because of clockwise sense, and so I got m L square d square theta dt square equals to minus mgl sine theta. One of the L's cancel out, and so you have a d square theta over dt square equals to minus g over L sine theta. This is a very hard problem to solve. Theta is a function of time because it's changing with time. So this is a hard differential equation to solve, but for a small angle it is actually possible to solve for it. So theta is small, we say sine theta can be replaced by simple theta, so d square theta over dt square minus g over L theta, and this is easy to solve. Can be theta at any time is some a cosine square root of g over L times t plus b times sine square root of g over L times t. So this is a solution of this problem. We'll talk about solutions like this. This is called simple harmonic motion equation. This equation is very famous, and this solution is very famous, and you probably should study it or see how I got it. You may plug in back in there and see satisfies that. If you don't have skill to solve this kind of equations yet, you can just say this is the answer, see if this satisfies that. Of course doesn't prove, but this you can check. This is on the left side and on the right side is equality. Okay, I think I'm going to stop here, and from next video onward I'm going to start doing problems from my book, and I'm not going to do theories like I did in the last couple of videos. Talk to you later. Bye.